So welcome to another lecture of the series of modeling and design of DC-DC power converters. So in the last lecture we have analyzed the discontinuity or the discontinuous mode of operation, which is called as DCM in DC-DC converters, the basic second order DC-DC converters like buck boost and buck boost converters. So we started with defect of no load. What happens to the response of the converter when the converter operates on no load? That the amp second balance is not valid, means it is not maintained, and thus it results in accumulation of voltage or increase of the voltage across the capacitor continuously. In buck converter it is not a problem because V0 is the max Vin. So V0, the maximum value of V0, so the capacitor voltage will keep on rising and reach a threshold of Vin, and thus it is safe. But for a boost and buck boost converter, V0 is Vin by 1 minus Dmax. So Dmax is 1. So it can go up to infinite voltages. Means not theoretically, but not practically, but means only mathematically it should go infinite. But it will be very high. So we need to design the capacitor in such a way that the capacitor will be able to take those voltage, that build up of voltage. So the solution to have or to get rid of the voltage build up or the amp second imbalance in boost and buck boost converter is to have a minimum load across the resistor. The minimum load we have calculated, and also we have introduced the reasons of the reasons for discontinuity, and we derived the expression of critical inductance for each of the converters. In today's lecture we'll see the steady state waveforms or the steady state analysis of DC-DC converters in discontinuous mode. So DCM operation of DC-DC buck converter. In buck converter, the switch is placed at the input side. The diode is placed in parallel with this configuration. Inductor is placed at the output side acting as a LC filter, and then there is a load. We'll assume that there is a load, and the discontinuity is due to the value of the inductance, that is L, where L is less than L critical. This is R, this is C, this is IC, this is I load, this is IL, this is ID1, this is IS1, IS1. So let's draw the waveforms for this converter. We'll start with the gate pulses. So I'll draw only the two cycles. So this is 1, this is 0, and this is for S1. This waveform is for S1. Or let me redraw it again. So 1, 0, this waveform belongs to S1. So let's draw let's go to the inductor and draw the waveform of the inductor. So we'll first start with the inductor current. So as you know that it is discontinuous in nature, the inductor current in the on time it will start from this point to this point, then it will fall like this, and then it will be clipped off. So I will draw using a separate color, so it will be like this. It will rise and it will fall before even start of the next cycle, and then it will be constant. Then it will rise, it will fall again, rise and fall. This waveform belongs to IL1, IL, the inductor current. Now drawing the inductor voltage. So when the switch is on, the voltage across the inductor is V in minus V naught, which is positive. So it will be like this. V in minus V naught, same V in minus V naught, V in minus V naught. When the switch is off, that is during this time, the voltage across the inductor when the diode is on, when the switch is off, is minus V naught. So it is minus V naught. And what happens when the switch as well as diode is off? That is, let it as state 3. What happens in state 3 is that so what happens here in this case is that I'll draw IL like this. IL becomes 0 because there is no path for IL to flow. So what happens is, this is plus minus V in, this is VS1, this is VL, and this is V0. If you apply KVL, it will be VL equals to V in minus VS1 minus V0. What happens is that in this case VS1 equals to V0, because when the switch was off and when the diode was on, then VS1 was V, VS1 was V. So instead of writing like this, I will say, so here what happens is IL becomes 0. Forget about the VS1 drop. So VL is L dIL by dt. So V should be 0. So the voltage across the inductor should be 0. So it will be like this. Oh, it should be like this. So this is minus V0 and this is 0. So during the third state, the voltage across inductor and the current in the inductor both are 0. So this waveform belongs to VL. Now we'll go to the next element, that is the switch. That is the switch. Now if we apply KVL here, so we'll separate this section like this. So VS1 becomes V in minus VL minus V0. This becomes 0. So this becomes V in minus V0. this drop is observed across the switch V in minus V naught Vs1. So initial, so we'll okay, first I'll draw the so we'll draw the voltage across the switch. When the switch is on, voltage across it is 0. It becomes 0. When the switch is open and the diode is forward biased, the voltage across it is plus V1. So I'll draw like this, V in. This is V in and this is 0. What happens when the switch and the diode both are off? Then Vs1 is V in minus V naught, which means it will be slightly less than V in. It should be like this. This value is V in minus V naught and this waveform belongs to Vs1. Vs1. So this we can close like this and let me bring down this new dotted lines. So now we have drawn the voltage across the switch. Now we will draw the current through the switch. The current through the switch will be, in the third state the current will be IS1 will be 0, IL1 is also 0, ID1 is also 0. So what we'll do is, when the switch is on, the current in it is IL. So I will use the same color as that of inductor. So like this. When the switch is off, the current through it is 0. So it is like this. Suddenly falling down. What is the value of the current when both the device and switch are off? It is still 0, so it will be continued like this. This waveform belongs to IS1. Switch is done. Now inductor is done, switch is done. I will go for the diode. So when the switch is on, the voltage across the switch is on, the diode is off, the voltage across the diode is minus V in. The voltage across it is minus V in. Oh. This value is minus V in because VD1 is plus minus this. So the voltage across the diode is minus V in. When the diode is on, voltage across it is 0 logically. Um, so here VD1 you can write as VL plus V0, where VL is 0, so VL will be V0 plus V0. So voltage across that will be plus V0. So it will be this is 0 and this is V0. This waveform belongs to VD1. Now we'll draw the current through the diode, which is ID1. If the switch is on, the current in the diode is 0. So here we'll draw this as 0. This we can further extend it to the left side. Similarly, this waveform we can extend toward the left side. To make the symmetry, so we'll go with the voltage, the current through the diode. When the switch is on, diode is off, the current in it is 0. We have already noted. When the switch is off, diode is forward bias, the current through it is IL. So we have to draw IL. It is a falling slope. I will erase this. And the current through the diode is still 0 when the diode and switch both are reverse, means both are off. So this trend continues. This current is ID1. Now we'll go to the last element, that is a capacitor. What happens in a capacitor? We'll draw the capacitor current. So the capacitor current is nothing but the inductor current brought down. So we will bring down the inductor current waveform by a value equal to the load current. So it will be like this. Till here and then 0. This will be the capacitor current waveform. This will be IC. This value is what? This is I load. And this, so yeah, I forgot to write one thing. So this is A1, this is A2, and this, there is no A3 actually, but A3 is this area, means which is 0, which has 0 value. And we'll write the time instances T on, T off, and like that. So Now we'll draw the last waveform, that is the voltage across the capacitor. So it will be, I'll draw in black only. So that is nothing but VC ICC dV by dt. So VC is 1 by C integral IC dt plus V naught. So I have to integrate this. Integration of this thing, straight line, is a parabola with positive curve, and for negative slope is negative curve, and for the zero or for constant value it is a straight line. So a rising parabola, a falling parabola, and this is a parabola and a rising edge. Rising parabola, falling parabola, and then a rising straight line. Again a rising parabola, a falling parabola. So this is the delta V naught. Delta V naught. This waveform belongs to V naught. So like this we have drawn all the waveform. So these are the waveforms of the buck converter. Now we don't know what are these times, so we will define these times. So this is T on. This time, say it is T or 2, and this time it is T3, or let us write this also as T1. This will be T1. Now actually T1 plus T2 was supposed to be our T on. Let me verify it. Yeah, T1 plus T2 I'm sorry, T1 is T on. So T1 is T on. Now T2 plus T3 was supposed to be our T off. Okay, because it is and this whole T1 plus T2 plus T3 is a T switching. So I'll write like this: T off, and this is whole T switching. So this is the case. Now apart from the steady state duty ratio D, we have to define one more duty ratio, because now there are 3 times, T1, T2 and T3. So let's define T on is capital T into T switching. T off, which was our previous assumption, that is 1 minus capital T into T switching. say that T2 is some D dash, because D1 is already our diode, that is D dash into T switching. So T3 will be what? T of minus T2, which is 1 minus D into T switching minus D dash into T switching, which will be 1 minus D plus D dash into T switching. Like this I have mentioned. This is T3 time. T1 is this, T2 is this, and T3 is this. Now we have to derive all volt second and current second balance in terms of D and D dash. D dash into T switching, which is T2, is the time, or let's do the reverse thing. Let's call it as T3. So let's say that T3 is the time where reverse as well as diode is turned off, that is D dash into T switching. So I will write here T3. So T3, T of minus T3, which is T2. So T2 is 1 minus D plus D dash into T switching because T1 is D into T switching. T1 is T1 only. T2 plus T3 is T off, which is 1 minus capital D into T switching. We assume that the last time, that is T3, is some D dash T switching, because that is additional term which came. So T2 we can write as T of minus T3. Now using the volt second balance, so A1 A2 A3, so T1 A2 T3. Similarly for the capacitor current, what we have is this thing. So means basically what we can write here is this we can write as A4, and this whole thing we can write as A5, because the positive area equals to negative area. So A4 equals to A5 we have to write. In previous case, so we know that in previous case this is T switching by 2. Why T switching by 2? Because the capacitor current wave, the inductor current waveform is exactly shifted down by its average value. Now here the additional time term came, but still this will be equals to T switching, and the period starts from here to here. So this whole, I can't write it here, I'll write it here. This whole is T switching. This whole is T switching. So what happens in this case is we have shifted for the amp second balance, we have shifted the time periods like this, but T1 was this time here, which you can see, but we have to start from this period. So we have to find this time, that is the time for A4, which is already T switching by 2. Which is T switching by 2. We have to find this whole time from here to here, which is what? This is whole T switching. So this should also be T switching by 2 from here to here. This is also T switching by 2. But the issue comes, so this A4 is a triangle, we can write half into base into height. But A5 we have to split, so we have to split it into 3 shapes. A5 has two triangles, which you can see here, two triangles and a rectangle. We should know this value, at least two of them we should know, so that the third one we can write T switching minus A minus B, like this. Let's say if this is A, this is B, then we can find it T switching minus A minus B, and then we can write for a triangle it is half into base into height. Height we know, that is I load, and base only you have to find A and B you have to find, but it seems slightly complicated to find. So what we'll do is, as volt second balance is easy to find, what we'll write is V0 by V in equals to I in by I load, which is also equals to I in by IL, inductor current. We know this transfer function will find this is M of T, and then we can easily find using amp second balance, because amp second balance gives us this current gain. So this first we'll find using volt second balance. So volt second balance is that A1 into T1 plus A2 into T2 plus A3 T3 becomes 0. So we have to do volt second balance. We have to see the areas in the graph of voltage across the inductor. So A1 A2 we have, but A3 is 0. So so A1 is what? V in minus V0 into T1. V in minus V0 into T1, that is T on, that is D into T switching, or let me write it as T1. V in minus V0 into T1 plus A2. A2 is minus V0 into T2, minus V0 into T2 plus 0 into T3 equals to 0. So now substitution, V in minus V0 into T1 is D, capital D into T switching minus V0 into T2. For T2 we have the big expression, that is 1 minus small d plus capital, means not small d, capital D plus capital D dash whole into T switching equals to 0, or I can write equals to this. I can cancel T switching and then find send this V0 term towards the RHS. So in RHS the terms remaining are V into D equals to V0. If I take V0 common, so it will be D plus 1 minus D minus D dash. So this gets cancelled. So RHS becomes V0 into 1 minus capital D dash. So therefore V0, the expression for V0 is D by 1 minus D dash into V in. This is the DC transfer function for the buck converter operating in the discontinuous conduction mode. So therefore M of D is capital D by 1 minus D dash. It is a function of two terms. Now D lies from 0 to 1, we know. Then we have to see D dash. So T3 was D dash into T switching. So D dash can vary from what? It can vary from T off to 0. D dash can vary from 1 to 0, because this portion here given by T3, this portion T3, the maximum value of it can be whole of T off and the minimum value can be 0. So T should be 0, so and T off is 1 minus D into T switching. So I can write it as in this way. T3 lies between what? 0 to T off. 0 to T off. If I substitute 0, T3. T3 is what? D dash into T switching. So T off. That is 1 minus D into T switching. This gets cancelled. So it gives me 0 less than D dash is less than 1 minus D. This is the range of variation of the D. This is a DC transfer function. Also, in this case, this value is delta IL, peak to peak ripple, and this is delta V naught. We have already drawn delta V naught. So same transfer function we can write for d by 1 minus d dash is what? I in by IL, without doing the amp second balance. Now there is one more way in which we can derive this DC transfer function in terms of the critical inductance. Now we can we cannot straightforwardly plot m of d versus a function of d, because we have a d dash term. We know what is the maximum and minimum range of variation of d dash, but it is not straightforward. We know only d. So the thing is, we have to describe d as a function of some other thing. We have to replace d dash with known terms. We have to replace the d dash with the known term. So we have to see how we will do it. So using the expression of inductor, let's see how to do this. So in this case, L is already less than L critical. So in the last lecture we saw how to find L, and L was maximum of L critical plus L found using the delta L expression. So in this case, L is already less than L critical. That's why it is a discontinuous conduction mode. We don't care about what is the load on the converter. So we'll find out, we'll see what is the L found using the delta L principle. So we know that VL is L DIL by dt, that is L delta IL by delta T. So we can either write in terms of so T2 and T3 has the d dash term, T1 has d term which is known. So we have to write for T2 or T3. There is no meaning in writing. So here VL can be VL1, VL2 or VL3. It can be VL1, VL2, VL3. This is for T equals to T1. This is for T equals to T2. This is for T equals to T3. And we can write as L delta IL by delta T is D into T switching, or T1. This is L into delta IL by T2, and this is L delta IL by T3. Now the value of voltage we can, so this is known. T1 is, this is T1. So T1 is known, D is known. So there is no meaning of writing in terms of when T is T1. So this will not use. Similarly for T equals to T3, VL is 0. Voltage across the inductor is 0. So there is no meaning of using this term. So we will use this term. We'll take VL2 equals to L delta IL by T2. So what is VL2? VL2 is same, that is minus V0. So here we'll take mod of it. So V0. So this is V0. We'll replace T2 with its value in this expression. So we'll write this in terms of T2. So therefore L into delta IL by V0 is equals to T2, which T2, where T2 is equals to this one, this whole expression, 1 minus D plus D dash into T switching, or we can write divided by F switching. Now we can write D dash in terms of this. So therefore 1 minus capital T plus D dash equals to what? 1 minus bracket capital D plus D dash equals to F switching into L into delta IL by V naught. So d plus d dash is what? 1 minus F switching L delta IL by V naught. So from this expression we can write d dash as 1 minus d minus of F switching L delta IL by V naught. This we have derived. So let's assume that using this formula we derived the inductance, but we also have to make sure that L in this case, so if we write this expression in terms of L, L will be what? It will be V naught T2 by delta IL. This we have to make sure that this L is less than L critical, which, so let's say that V naught is same as discontinuous mode as well as continuous mode, and delta L is also same as discontinuous versus continuous mode. So this T2 will make sure that the value of the inductance is less than L critical. So there is no need to make sure this expression of this we can, this which is V naught into T2 by delta IL, this should be less than L critical, or we can write V naught T2 by delta IL should be less than L critical. What was L critical? For buck converter is R into 1 minus D by 2 F switching. R into 1 minus D by 2 into F switching. This we have to make sure. So T2 should be less than R into 1 minus D into delta IL by 2 V naught F switching. Writing, so further what you can do is this, if on substitution of T2 on T2, if substituted, we get a range of variation of d dash, which we want to find, but we have already found the range of variation of d dash, that is d dash lies from 0 to 1 minus d. So there is no need of solving this equation. This equation we will use d dash in terms of this. So therefore equation number, let's say this is 1. So and okay, let's write this as equation number 1. This is also equation number 1, and this, let's write this as equation number 2. So using 1 and 2 we'll write in terms of 1 minus d dash. So 1 minus d dash, what was 1 minus d dash? 1 minus d dash was d V in by V naught, d V in by V naught. So on rearranging 2, if we rearrange 2, what we get? 1 minus d dash. What was 1 minus d dash in this equation? In this equation, what is 1 minus d dash? 1 minus d dash is equals to d plus F switching, capital T plus F switching L delta IL by V naught. This is after rearranging. So 1 minus d dash is d plus F switching L delta L by V naught. So equating this, what we'll get? Therefore d into V in by V naught equals to capital D plus F switching into L into delta IL by V naught. So if you multiply by V naught, it will be dV in equals to dV naught plus F switching L delta IL. So what is V naught? 1 by D dV in minus F switching L delta IL, or it is V in minus F switching L delta IL by D. This is the expression of V naught in terms of the system parameters. So as F switching L into delta L by D is positive, so V naught is less than Vin, which is valid for a buck converter. So V naught by Vin, if we write V naught by Vin, it is if we divide this equation by Vin, it will be 1 minus F switching L delta IL by D Vin, which is M of D. So this equation we can plot, but this is for some different values of Vin. So plotting M of D for CCM and DCM for the same operating conditions, that is same R which is or I load, V in, F switching, capital D, delta IL, delta V naught, and so on. We have to just compare that for the same operating condition, which mode of operation, DCM or CCM, gives the highest gain, and that too for which duty ratio thing. So if we plot this is D and this is M of D. So for this thing, so this is 1, this is 1.50, yeah, y equals to mx, so it will be same. So this was for this is for CCM. Now I'll draw for DCM. For LC, for this is this waveform is independent of what? L, F switching, independent of L and F switching. Now if I draw this waveform, what happens is, in this waveform, as the duty ratio is less, so initially this value will be very high. So this expression for the low duty ratio, the gain V naught by Vin will be more for DCM rather than CCM, and it is not a linear thing, it is 1 by this, so it is non-linear. So we'll have some higher gain like this, the gain will keep on changing like this, but as the duty ratio tends to 1, so as D is higher, the value of this expression will be this is what you can say considerable for lower D, and for higher D it will be less than 1. So the gain will be less for higher D. For what? For higher duty ratio. So it will be like this. So like this somewhat will be the these points I will just rub. It will be like this, somewhat like this. So there will be some intersection point. So at this intersection, this is for DCM, this is for L1, this is for one value of the inductance L1. As the inductance changes, so what happens as the inductance changes, this drop which is subtracted from Vin will be increased. If we increase L, the drop in Vin is increased, which means that the V naught by Vin gain is reduced. So this is DCM for another inductance L2, and this is for DCM for another inductance L3. So out of these all, L3 is greater than L1 is greater than L2. So what we observe is that DCM gives more voltage gain, or M of T, for low duty ratio and less gain than CCM for higher duty ratio. And in DCM itself, as L increases, M of T will decrease. This is the observation. So apart from the voltage gain, there are other different comparison criteria for which we have to compare the operation of discontinuous versus continuous mode. So discontinuous mode in buck converter, so it has further advantages like the reduced losses. It will result in soft turn on and less electromagnetic emission. This is electromagnetic emission around, it will come in the isolated converters. So the DCM mode of operation has its own consideration. So this you saw in this lecture we saw the steady state analysis for the DC-DC buck converter. We can use the similar approach for a boost converter and derive basically. So we'll see in the next lectures about higher order DC-DC converters. So the operation of boost and DC-DC buck boost converter in DCM mode, this you can try in your own, and you can draw the waveforms. You can derive the ratio between T1, T2, T3. You can write M of D, then you have to replace D dash, and again replace it in terms of the known parameters. Put a limit on D, solve for D dash, write D dash, write limits for D dash, put L less than L critical, put the basic formula of L to replace D dash in terms of the known parameters, and then ultimately find the gain, and then you can plot the gain characteristics. So this analysis you can do for the boost and buck boost converter. So for this steady state DCM analysis for the DC-DC converter, the assumption is that there is a load on the converter. The only thing is that L is less than L critical. So we are done with the discontinuous operation of DC-DC converters. In the next subsequent lectures, we will analyze the higher order DC-DC converters. After that, we'll see isolated DC-DC converters. Thank you. So one more thing to note in this case is that this was the IL for continuous conduction mode. Now IL for discontinuous is the waveform gets clipped off. So it is somewhat of this nature. It is like this. Or what you can write is, or if you clip this portion, then you will get the waveform as like this. It is clipped here. So like this. So what happens is that as this portion is clipped off, so this was delta IL. But while deriving the delta L for discontinuous conduction mode, we have taken as this as delta L. This is not the delta L. Delta L is this whole thing. So this whole thing is delta IL. So this new thing should be delta L of D, that is in the discontinuous conduction mode. This is the delta L of T. So in discontinuous mode, you have to replace all delta L with delta IL of D. So this should be delta ILD, DILD, delta L of D, delta L of t. Everywhere you have to write delta L of t. So this is delta L of d. Now again the thing is delta IL is not known to us. We should have all the terms in terms of the plant parameters which are directly known to us. So again we have to replace delta L of d in terms of the known plant parameters. So first we replace for discontinuous mode, wherever there occurs a delta IL, we replace it with delta L of d, because for discontinuous mode delta L of d is there, and delta IL of d is less than actual delta IL, which is for the continuous conduction mode. I think I have replaced all delta IL with delta IL of d. So here let me write d. I think now everything is replaced. So now we can further solve it. Yes, everything is replaced. So therefore delta IL of d should be less than delta IL. Okay, this is there. So we need to replace delta L of d in terms of known plant or system. System is here the converter. System parameters. So how to write? We know that the average value of the inductor current for discontinuous mode is equals to the load current. Even if it is continuous or discontinuous mode, average value of inductor goes to the load because of the connection of the inductor. The inductor is connected near the load, so its average value goes to the load, whatever is the type of the waveform, discontinuous or continuous. So if we see average value, this waveform you have to see, this IL waveform. So here its average value is, so this triangle, just area under the, so how you find the average value? Average value of IL, which is equals to capital IL, is 1 by T integral 0 to capital T switching. I'll write T switching. So IL of T dt. This is the average value. But this, what is this? This is the area under IL versus time graph. So you can write as area into F switching. What is the area? We can write this area now. This area. So this is the triangle. The area is what half into base into height. What is the base? It is T1 plus T2. It is T1 plus T2 because the triangle is spanned over T1 plus T2 and the height is delta L of T, which is mentioned here. So we can easily write it as, therefore IL is F switching into area. Area is half into base. What is base? T1 plus T2. Height is delta IL of T. So we replace delta IL of T from this expression. So therefore delta IL of T becomes 2 capital IL by F switching into T1 plus T2. Now if you substitute T1 and T2, we'll get 2 capital IL by F switching into T1 is D into T switching. So D by F switching will write D by F switching plus T2. So what was our T2? It is a big expression. So it is 1 minus of T plus T dash 1 minus D divided by F switching. So the whole denominator is this by F switching. This is thing, the F switching gets cancelled. This is 2 capital IL by, so D minus D will get cancelled. So it is 1 minus D dash is delta IL of D. This we got from this expression. And what is capital IL? It is I load. So this is not the ultimate expression, so I will write equals to 2 by 1 minus D dash into IL is V naught by R, so V naught by R, 2 V naught by R into 1 minus D dash. This is the expression for I. Now we have again derived D dash in terms of D dash again we have derived in terms of this, in terms of D and this. So we can substitute it in this expression. We have derived the expression of delta L of D in terms of D dash. But still we don't want D dash and we don't want delta L of D. We want everything in terms of known parameters. So that's why very quickly what we'll do is, in this expression, so this was the critical inductance, and this is delta IL. So critical inductance is where IL minimum is 0, that is L equals to L critical in this case. For this case, discontinuous mode, this whole is what? This is delta IL and this one is delta IL of D. So we can write VL is L into delta L by delta T. So if we assume that VL and delta T are constant for a given on time, so we can say that L into delta L is constant. So therefore L1 into delta I1, so let's say this is for one case, equals to L2 into delta 2, this is for other case. So this is case 1 for critical conduction mode, case 2 is for discontinuous conduction mode. So therefore L critical into delta IL will be L or LD, you can write. So here L equals to LD, remember L equals to LD. So L critical into delta L equals to LD into delta LD. So we can write delta L of D as L critical into delta L by LD. Or if we replace L critical, we'll get R into 1 minus D by 2 LF switching. Let me check. L critical for a buck converter. Yeah, R into 1 minus D by 2F switching. So R into 1 minus D by 2 into F switching. This we substituted here into delta L into LD. So this is equals to delta L of D, and delta L of D we can substitute from this expression, that is delta L of D equals to 2 V naught by R into 1 minus D dash. So 2 V naught by R into 1 minus D dash is R into 1 minus D delta L by 2 LD into F switching. So we find 1 minus D expression, 1 minus D dash as 4 V naught L F switching by R square into 1 minus D into delta L. Now this right hand side in terms of the known parameters. Okay. So this is known to us. Now we'll use the basic equation of V naught and V in terms of D and D dash. So V naught was D into V in by 1 minus D dash from equation number 1. If we substitute the value of 1 minus D dash in equation number 1 will be modified as this equation. This is delta L This we put in, substitute in equation 1. So this is equation 1 modified. So V naught is dV in by 1 minus d dash. So 1 minus d dash is this inverse. This is this. So r square into 1 minus d into delta L by 4 V naught L F switching. So V naught, if we bring here, it will be V naught square equals to r square into t into 1 minus d into delta L into V in by 4 L F switching. Now if we multiply and divide, if we multiply with V in from both the sides, we'll get V naught square by V in square, or V naught by V in is square root of this term, the remaining term. The remaining term is r square. So r square I brought outside, it will be r into under root of d into 1 minus d into delta L by 4 L F switching into Vn, because 1 Vn will be there. So this is the m of t, which is r under root d into 1 minus d into delta IL by 4 into L into F switching into Vn. So in terms of L critical I have written here, or we can keep this equation in terms of L critical also. So this is the ultimate equation, final equation, ultimate DC gain. If we plot this, then we'll get these characteristics which are mentioned here. That is for less duty gain. Now delta L for discontinuous and delta, so this delta L is for delta L for continuous conduction mode. V is known, F switching is known, L is known. L is the normal inductance taken. We can easily plot m of d for discontinuous mode and continuous conduction mode, which I have already plotted here. And what we observed is that DCM gives more voltage gain for lower duty ratio and less gain than CCM for higher duty ratio. And that's why for the buck derived converters, where there is a limitation on operation of duty cycle, that is when you have to operate in lower duty ratios, then discontinuous conduction mode is preferred. For example, in forward converter is a type of buck derived isolated DC-DC converter, which is used for supplying auxiliary supplies in any power converter device, say in SMPS based devices. So discontinuous conduction mode has its own benefits. So with this lecture we concluded the discontinuous mode of operation for a buck converter. So similar analysis you can do on a boost converter and buck boost converter and derive the DC gain and do the voltage and current, you can do the voltage volt second balance and the amp second balance. So in this lecture we derived the condition of discontinuity using the L critical, where L is less than L critical. We derived the equation of, we assume there is a new time or a new state, that is A3, this time T3, which is some D dash time T switching. With this we got delta IL of D, which is not equal to delta L, which is less than delta L. So our aim is to replace delta L of D and D dash in terms of the known parameters. We did all types of simplification, and we ultimately came to know that we succeeded in replacing delta L of D and D dash in terms of these known parameters, where at least delta L of D should be known. So if you compare the MD with DCM with CCM, you can put the same value of F switching, V in, delta IL. The only thing that will change will be LD. L will be LD. And MD for CCM is what? It is just D. It does not depend on R, load resistance, or any other thing. So as you know that inductance is the function of delta IL. So as inductance changes, delta IL also changes. So if you want to compare the M of T for any converter, say for a buck converter, for CCM versus DCM mode of operation, you have to make, for comparison, of M of D for D, that is for DCM, with m of d of c. That is for CCM. The assumptions are both these modes should have equal what? We are comparing this with respect to duty ratio variation, so we can't keep duty as fixed. What we can keep equal is f switching v in. V out we are not changing because V out is a function of V in. What else? FSW V in. This we have to keep constant. Now the change, now what we already know the reasons of DCM. So we have to select only one reason for DCM, that is LD is less than L critical. So if LD is less than L critical, and if you want to compare M of T for DCM versus CCM, you have to keep L as constant. By assuming some value of L, we have to compare MD of D versus D. Sorry, we have to compare MD of D, MD of C, that is for MD for discontinuous mode and continuous mode. We have to plot this versus duty ratio for different value of inductances, and for all the value of inductances, M of D for continuous conduction mode will be constant, which is D only. So this we have to plot for various D. We have to plot this for different LD. This we can plot for different LD. You can't keep inductance as same for both the DCM and CCM for comparing for DCM and CCM, because if you put LD less than L critical for even continuous conduction mode, then that can result in discontinuous conduction mode. Then what you have to do is you have to increase the load for it to operate in continuous conduction mode. But then again, we are comparing with the same power level. So and what we have to write here, I have to write I load. So you can't keep L of CCM with LD. This you can't assume. So you plot M of T versus D and M of T of C versus D for different inductances. And what you know is that if the value of inductance increases, M of T will decrease, which was correct when we derived this thing. For a given D, so here for a given D, M of T will decrease when the L increases, which is valid here. And for lesser D, M of D for discontinuous is greater than M of D for continuous. And the nature of M of D versus D will be mostly equals to, so it is non-linear in nature. So what I'll just draw a table I'll just quickly draw a table D, and this is M of D for D 0, 0.25, 0.5, 0.75, 1. It will be 0. If D is 0.5, so 0.5 is 1 by 4 into 3 by 4, it will be 3 by 8. So let's write M of D for D as some K under root D into 1 minus D, because we are plotting against only D. So it will be K square root of 3 by what? 1 by 4, na? So 3 by 8. For 0.5 it will be K under root of 1 by 4, that is K by 2. For 0.75 again it will be K root 3 by 8, and for 1 it will be 0 again. Like this will be the variation of the duty ratio with respect to the time. So it will be somewhat like this. And M of T for continuous conduction mode, whatever was the value. So if for 0 it is 0, for this it is 0.25, for this it is 0.5, for this it is 0.75, and for this it is 1. Why? Because M of D is D. So whatever is D, that will keep on pasted as it is. Now we have to compare which is greater. Here both are equal. Now this is k root 3 by 8. K is what? What is k? Where k is r square root of delta I, r square root of delta L by this 4 we can keep out and we can erase it. Like this we can write r by 2 square root of delta L by L of t into f switching v in, which is some term, which is some equation. So this we have to compare that k is greater or d is greater, because this equals to d, this equals to d, and d you have to compare. So what we observe is that this is greater than equals to d for lower duty ratios. If you plot like this, this is d and this is m of d, 0, 0.5, 1, 0.75, 0.25. First we'll draw for the so 0.25, 0.5, this is 1, this is 0.75, 0.25 to 0.5, 0.5 to 0.5. It is not up to the scale, but you can draw it. So this is for this, these three lines. It is a straight line. This is m of t for continuous conduction mode. Now if we draw for discontinuous conduction mode, it will be 0. So here we can write as k is a function of L, and as L increases, k decreases. This we should know. So for 0 it is 0, for 0 again it is 0. So it is somewhat like this. So this is for some L1, this is L2, and this is L3. So what we know that L3 is greater than L2 is greater than L1, and these three curves are MD for discontinuous conduction mode. So you can find the intersection point at which MD becomes less than MD of D becomes less than MD of C, which you can easily find using solving this equation. So this was the analysis of the discontinuous conduction mode of a DC-DC buck converter. So similar analysis you can do for boost and buck boost converter using your own understanding by taking help of this principle which we did for the buck converter, using the same approach and the same procedure. So in the next lecture we'll start about higher order DC-DC converter, that is second order DC-DC current controller, and how to derive higher order voltage controller. Now the converter which we studied till now was voltage converter, means it used to convert voltage from one level to other level. So you can call it DC-DC boost, buck or buck boost voltage type converter. In next lecture we'll see current type converter, that is second order DC-DC current converter, that is input source is a current source, output source is also so the output side we have a load feeding any current. So from that DC-DC current converter we'll see how to derive higher order DC-DC voltage converter, that is fourth order DC-DC voltage converter. Classical examples are Sepik converter, Chuck converter, Zeta converter, resonant converter, and so on. After that we'll see these isolated DC-DC converters. Thank you.